Okay, oh, this is very loud. Let me thank the organizers first to inviting me to this very nice meeting. And today, I'm Claudio Maggi. I work in the lab of Roberto Di Leonardo at La Sapienza in Rome. We mostly do experiments, but today I'm going to talk about theory mostly, and especially these works have been done in collaboration with Umberto Marini Bettolo Marconi, Nicoletta Agnan that is here, Matteo Paluzzi that is now in Syracuse in US, and Roberto, of course. Okay, so we're talking about active matter. What is active matter at the micron scale? What we study in the lab, what we study every day in our lab is mostly swimming bacteria, like Escherichia coli, you see here in this beautiful movie by Berg. Those cells can swim by spinning their helical flagella that they bundle together and they can propel. But sometimes the bundle gets disrupted and they turn, so they reorient. Another example of synthetic active particles is these Janus particles. They are plastic or glass microbeads. Coated, one half of their surface is coated with platinum or gold, and they catalyze the reaction of the breakdown of H2O2 that is in solution with water, so they can swim, because they create a phoretic slip flow around them, and this slip flow induces a stress on the particles, so the particles is pushed around. So we have active particles, and I want to convince you that these systems are very far from equilibrium, and to convince you of this, if it's not obvious, I want to show you these experiments that we did in our lab. This is with swimming bacteria. You have this microgear that is like 4 times smaller than the diameter of a human hair. It's made of plastic, it's completely passive, but then when you put it in solution with swimming bacteria, the swimming bacteria get trapped in the corner of the microgear and start pushing the gear all in one direction, mostly in one direction. You can do a similar experiment with these man-made Janus particles, and you see that they organize very well around the microgear and they push it in a unidirectional motion. And I hope this convinces you that these systems are really out of equilibrium, because you cannot have such a behavior in equilibrium, otherwise you would be violating the second law. So this we published. This is actually the very first experiment by Roberto, and this is more recent. Okay, so out of equilibrium, say goodbye to the Boltzmann distribution. And this is so, when you think about this, you realize that this is such a fundamental an important result of statistical mechanics. Actually, is really the core of statistical mechanics. And I like a lot the almost poetic image that Feynman gives of the Boltzmann distribution after having defined the Boltzmann distribution. He says, this fundamental law is the summit of statistical mechanics, and the entire subject is either slide down from this summit as you derive the many results in statistical mechanics, or you can climb it up and derive the Boltzmann distribution. So it's this image of a big mountain like Mount Everest. Unfortunately, with active matter, we don't have such a basic principle to build our theories on, and we have to look at the dynamics. But there are some models that we can study and see if we can find some information about the stationary distribution. That is the most important thing that you would like to have to describe a system with statistical mechanics. And actually, there is a model, spoiler. There is a model that is becoming very popular nowadays, and is the run and tumble model. And these models are built in such a way, we are overdamped, we have very low Reynolds numbers, so our equations of motion do not ever have inertia. So we just have that the velocity is equal to some force, that could be some external field, and some noisy term that represents the swimming, the propulsion of the particle. In particular, the run and tumble model is made in such a way that this is in 1D, is made in such a way that the particle swims straight for a given time, then it switches to the other direction, then after some time, at random times, it switches again going to the right. So you can think that your active particle is swimming left or is swimming right, and is instantaneously changing the direction of swimming. And the distribution of this run lengths of these waiting times is exponential, because the process of switching is Poissonian. And actually, this model was studied in the early 90s by Schnitzer, and then it was made popular again by Taillère and Cates that studied this in presence of external fields in a lot of different situations. And the good thing about this model is that we know the stationary distribution. You can solve the corresponding equation for the evolution of P and find the solution in the zero current case, in the stationary case with zero current. And you see it's very different from Boltzmann. And actually, if you start playing with it, you see very strange effects, like if you confine your active particle, your unentangled particle, in a harmonic potential, as you increase the correlation time of the noise, you will see a strong drift from the Boltzmann distribution. You see here, develops this peak at the border of the harmonic well. Very strange. Unfortunately, this model can be solved exactly only in 1D. So only 1 degree of freedom, only 1 particle, only 1 dimension. It's a little bit frustrating. So I decided to look at another model. This is it's an alternative model where now I write it in multidimensional form. Now the x is a vector, the x dot is a vector. I take the gradient of a potential. And then I have the noisy propulsion term, the noisy propulsion force, that instead of being run and tumble is produced by an Ornstein-Uhlenbeck process. So it's a Gaussian colored noise, what comes out of this equation, this auxiliary equation for the noise. And actually, the good thing of this is that it can be manipulated and can be rewritten as a one single equation like this, where I is the identity matrix. Nabla nabla is the Hessian of the potential. So nabla nabla is like an internal product here. It's a fancy notation that we use. And so you see, it's not that this in this form is simpler than this, but this is the starting point for doing approximations. And in particular, there is an approximation developed by Maggi at the end of the 80s, let's say. And this approximation simply consists in deleting this term, setting this to 0. And if you look at it, it's kind of intuitive what you do when you neglect this, because this plays the role of some sort of non-homogeneous friction. What? I pressed something that I wasn't supposed to. Okay. So this plays the role of a non-homogeneous friction. So if this is large, you can neglect inertia, like when you have the Langevin equation with inertia and you want to go to Brownian dynamics and you want to forget about the mass. Yes? Not yet, not yet. Well, yeah, but you're right. When you delete this and you want to, yes, and you want to write the corresponding Fokker-Planck equation, you have to interpret this as in the Stratonovich form. You can write the Fokker-Planck equation. And actually, this Fokker-Planck equation was solved by Maggi and other people in few dimensions, 1, 2 dimensions. And then I started playing with this, and I made a computer program in Mathematica that would solve this, that would integrate the Fokker-Planck equation in the zero current case for an arbitrary number of dimensions. And this is the madness that you get out of it. When you solve it in 1D and you get the result by Maggi. You solve it in 2D and you get this thing with a lot of terms here. You solve it in 3D, you get even more terms. And I couldn't put on the slide what you get when you go to 4Ds because the slide is not enough. That's the point. That's a good question, because this when you delete this, you are left with another dynamical equation with multiplicative noise that you interpret in a Stratonovich fashion. And so these solutions are exact for this equation, but not for the original equation with the mass. And this approximation works if tau is small, it works. You can prove that it's a good approximation, but it works also if tau is very large, given that all the eigenvalues of the Hessian are positive. Okay? So I was kind of lost at this point. I couldn't make sense of it. But then finally I realized that it has to be like this. So this is the solution. I was playing with this, and I was finding that this is the right solution for any number of dimensions of the Fokker-Planck equation associated with these dynamics. And you see here you have the potential, the square gradient of the potential, and this is the absolute value of the determinant of this matrix, that is the sum of the identity matrix plus this Hessian of the potential. Actually, I couldn't prove this, so I didn't have any expertise to prove this because I'm an experimentalist. So I went to Umberto and I asked, would you help me climbing this mountain? And we went on the mountain. You see, this is Umberto, ready for going on the mountain. This is me, this is Nicoletta. And Umberto, after a few weeks, came out with this proof that actually, if at some point you manipulate the Fokker-Planck equation and use the Jacobi's identity that I didn't even know it existed, you can prove that this is the solution of this of the Fokker-Planck equation associated with this. So this is in this paper. So okay, now we have this. It's very nice, and I'm gonna show some example of it. But before I do that, I must admit that I was quite surprised that we could publish so many papers with this, and that also other groups started working with it, because once you have the stationary distribution, you can derive a lot of results on the, of course, on the structure of the system, of the static properties of the system. In particular, you can here you see some papers that we made out of it, and but actually later we understood that we could also say something about properties that are now becoming a very hot topic in active matter, like the pressure. And more recently, instead, we are also, thanks to the work of other groups, we are understanding that this UCNA approximation is a little bit of a hybrid between, by studying the stochastic thermodynamics, we are understanding that this UCNA is a little bit of a hybrid between equilibrium and non-equilibrium, because you can show that the FDT is violated, but at the same time, you have zero entropy production. This was shown in this PRL, this NAS PRL. Then we made some other calculations, particular Umberto. So of course, I cannot talk about all these works, but I will just give you a few examples of what you can do with it, and what it means practically to go away from Boltzmann and what we expect from active particles. So let's take the simplest case ever. 1D. In equilibrium, you have Boltzmann. If you use the UCNA, you have this strange formula. And you see, now imagine that you have a repulsive potential, like r to the minus 12, x to the minus 12, repulsive soft potential, no? And you plug it in this. You see, these two terms will just tell you, okay, it's a little bit more repulsive than equilibrium, because in equilibrium you have that the distribution wants to stay away from the repulsive potential. But this term here, this wants to grow where the curvature of the potential is high, and such a potential has a very high curvature the more you go towards zero. So this is quite of counterintuitive. It's a little bit like repulsion becomes attraction, because you have a repulsive potential, but the probability wants to grow where the potential is high. Why? Actually, if you look at the dynamics, you kind of understand why. It's because the particles, as memory, decides to go straight in one direction, but when it hits the wall, it stops. So you have a peaking of the probability on the wall. And this is connected to what was told by our chairman a couple of days ago, that bacteria, active particles, they like walls. And this is one simple schematic model to understand this. It's just a statistical effect of the correlated force. And actually, the power of the theory is that you can be quantitative. You can run your simulation, this full line, and then you can superimpose the theory, and you see that there is some deviation, but qualitative, and also not so bad quantitatively. The theory captures the peaking of the probability on the repulsive wall. And while the Boltzmann distribution, that is this dashed dot line, would like to stay away from the wall, because that's where the repulsion is. Actually, we can even compute the pressure that this particle exert on the wall. You can see at the different values of tau. This red is small tau, blue is large tau. And actually, we can prove that the ideal equilibrium gas is an upper bound for the pressure of the, is an upper bound with respect to the active system. The equilibrium system with the same diffusivity will always exert higher pressure on the wall. And actually, we can even approximate this peak as a Dirac delta, and we can find the fraction of particles that stick on the wall, of course, non-interacting particles. And we see that it takes quite a simple form, because what really matters is the persistent length of the motion. That is a combination of the diffusivity and the persistence time. Yes? The integral of what? Here? Yes. Yes, sure. But it's not normalized here. There is just proportional, but you have to compute the partition function, of course. You have to compute the normalization. This is actually this. When the wall is very steep, the normalization is this. This is the integral of this when the wall is very steep. So actually, this is a very, opens another because, well, okay. So, okay, this is intuitive. So the theory embodies an intuitive idea of the dynamics, that the dynamics is persistent. If you hit a repulsive wall, you stop there, probability increases. Fine. Okay, let's go to more dimensions. Okay, let's suppose we have a central potential, like our particles are confined in a circular container. If you do 1 or 2D in equilibrium with a central potential, nothing changes. I mean, you just have to be careful and integrate this in R, dr, but basically the probability distribution is the same in equilibrium when you do a central potential, right? You can go to 1D, 2D, 3D, just have to be careful with the integral, but it's the same. Here the things change. You have an extra term. If you do it 1D, then you go 2D, this guy pops out. And actually this is going to tell you if this is positive, as it is if you are inside the circular wall. This tells you it's even more attracting. The circular wall, it's even more attracting. And this is a little bit less intuitive of what we have seen before, but you can make sense of it if you look at the dynamics again. Because if the circle is very small, if the confining circle is very small, the particle can turn in the wrong direction and go against the wall once again. So again, you find an intuitive explanation of what the theory is telling you. If you look at the movie of the dynamics, the particle doesn't turn enough, turns just a little bit, hits the wall again, probability increases. So it's not that active particles just like walls, they like curved walls. They like walls, but they like even better curved walls. And this is just this term here, is represented by this term here. Again, we can be more quantitative, and now the theory works even better. And this is a confirmation of what I was mentioning before, that the more positive eigenvalues you have, the better is the theory, even if tau is very large. And again, you can make the calculation when this border is very rigid and approximate this peak and find equations that are analytic, because as I was saying before, the point is to integrate this to get the normalization. And this you cannot do you cannot do it in general, but you can do it if the wall is extremely hard. Then if you take the limit correctly, you can get analytic equations for the for the probability of finding the particle on the wall, because this becomes a delta. So everything is simpler, and everything depends only on the persistence length. That is a combination of speed and the persistence time. So that's okay. But now I made only a few degrees of freedom. Now I want to switch to more degrees of freedom in the next example. It's very recent work we were doing. Let me tell you before I move to that what I'm saying is we kind of see it in experiments. We see that particles like walls. In particular, there was this experiment of the group of Wilson-Poon in Edinburgh that showed that bacteria that are these green things here like to accumulate on the border of droplets. They make liquid droplets in oil, and then they have fluorescently labeled bacteria, and they go hit the wall and they stay there for a long time, and you see probabilities peaked on the wall. So this is qualitatively in agreement with what we see. And also we did experiments, and also everybody that works with bacteria knows that on the walls there are a lot of bacteria, so it's very debated. This is hydrodynamics, it's statistical mechanics, but at least our model reproduces this. So, okay, many degrees of freedom. Okay, active matter is kind of divided. There are people studying birds and flocks, and people studying bacteria, and one of the most popular model for describing the birds flocking is this Vic-check model, where you have particles that want to align, and they also move. And actually, recently there was a nice paper by the group of Chate that said, oh, look, if you put colored noise in the angular degree of freedom of your Vic-check particles, you get very rich phase behavior, very exotic phases, very interesting. On the other hand, the group in Rome, with Irene Giardina, they kind of found that the interactions in these bird flocks are topological. So even if the network changes a little bit, the interactions will be the same, because they don't depend on the distance, they depend on the hierarchy, let's say, of your neighbors. So we said, okay, maybe we can, and they also use this lattice model to interpret their data. So we said, okay, maybe we can put these things together and think of a colored XY model. So now the variables are the phases that are coupled to the standard ferromagnetic interactions. But now the forcing noise is colored, is our Gaussian colored noise. And actually now the calculations become heavier than what I've shown you before, but I can tell you the results. And within the UCNA, by just using that formula for the probability, we can derive many results. Okay, first of all, let me tell you what happens if you simulate these spins, these little compasses with color and noise. What you see is that as you increase the memory of the noise, the system is much more correlated. This is the XY model with standard nearest neighbor interactions in 2D. You see that when you change the memory of the noise to 0.1 to 1, you see a very qualitatively different behavior of the system. Here you see that also, if you don't like to look at, oh, spoiling again, damn it. I'm pressing something wrong on this. Okay. 5 minutes. Oh yeah, I'm finished. Okay, so if you don't like to look at the simulation directly, you might look at the distribution of the phase. You see that here is very peaked, here is very broad. Now it would be very hard to say something just by looking at the dynamics, no? Why is it doing like this? Why? I mean, you just look at this thing and you don't really understand what is going on. But luckily we have theory, and we can predict a lot of results. Like if we make into a fully connected model, and this alpha becomes 1 over n. So let's consider first the fully connected model. We can compute the phase diagram, and we can show that actually the critical temperature has to increase with the memory of the noise. We can find a new critical exponent because you can cross the transition line by changing tau. So we have a new critical exponent associated with tau, and it's 1/2. Okay. But what the take-home message is that the color of the noise tends to make the system more correlated, because you need higher temperature to destroy the magnetization. But we can also do calculations at infinite dimensions. And we can prove that there's no longer range order in 2D. But we can show that the vortex unbinding transition changes with the memory of the noise if the system has finite sides. If the system is infinite, the vortex unbinding transition temperature stays the same. But if the system is finite, you have again that the vortex unbinding transition temperature increases. No, it's the vortex unbinding transition, the topological transition. Now, when you have that isolated vortexes form everywhere in the XY model. Yes, but in the calculation, you're right. If you take the thermodynamic limit, it disappears. This shift in the critical temperature disappears. But we can do calculations with finite size corrections, and we find that the system has finite sides, this vortex unbinding transition temperature increases, but the way this change in the transition temperature dies out is logarithmic in size. So it's extremely hard to get rid of it. You have to make a huge system. So, okay, this was the last example I wanted to give you. And I hope you like this little hill we are studying. And you might want to just come and take a walk on this hill. And you know, you can take your favorite equilibrium model and just make it colored, make it active, let's say, and have fun with it. Because you know, little hills can be a lot of fun, especially if you have a dune buggy. Thank you for your attention.